Yeah, hello, madam.
Hello.
Uh,
Yeah, happy to answer any questions. Go ahead.
yeah, I had two questions. One was about that in the context of box similar method, you mentioned in the lecture about the density transformation, like one f of d theta is equal to determinant of Jacobian
Yeah.
into. So, can you provide some background around it? I mean, what is the basis for that transformation? How is it? How those two densities are equal with Jacobian being multiplied, determinant of Jacobian getting multiplied, and
Uh,
f of d theta equals to determinant of Jacobian into f of x comma y, right? So,
yes.
is it the transformation applicable for any density, any two density functions? And why is that that identity true?
Okay. So first, I can try and answer when is it applicable. So it's not applicable for for all functions. So if I have a function f that is not one to one, okay. So maybe I'll try and see if I can. Just give me 1 minute, actually. So let me see if I can share. Um, Okay, this. Okay, so if I have, you can see this, right?
Yes, yes.
Yeah. So if I have, let's say, a random variable x is a random variable, right? And it has a, PDF px. Okay. So if I have a function that's one to one g, then the transformation of variables equation can hold. Okay, so if I define g of x as this is my transformation of interest. Okay, so that means that if g of x is my new transformation, which is y, and x is a random quantity, so here I use capital. The capital means that this is random. Because this is random, this is also random. Right? So then y becomes a new random variable, and so a it should have a density, right? Density function, or we would expect it to have a density function. Okay, so again, the condition over here is that the function should be one to one. So it's not true for all functions. Does that answer your first question?
No, when you say one to one, for
Mm-hmm.
f of x, in the first f of x that you had put there,
Oh,
that
so
is
this
also
this f of x is a density function. So it's the PDF,
right.
right? This f of x, sorry, this g of x over here is the transformation function. Okay, so that's a different function. So
Okay.
for example, so let's say x is distributed, let's say normal 0 1, and I'm interested in uh, what is the distribution of x plus 5.
Hmm.
Okay. Now x plus 5 is also a random variable. It's a very simple transformation, but it's also a random variable that
Right.
I can call as a new random variable y.
Right.
And this random variable y is can be defined via x, right?
Yes.
So I have basically my g function over here, g of small g of small x is x plus 5.
Mm.
Okay, right? That is my g function over here. And the question is now this random variable, this is a random variable that has some PDF, right?
Yes.
So what is that PDF now? This is what we want to find, right? For this new mapped random variable, this new random variable, what is that PDF? This function, x plus 5 function, is a one-to-one function, right?
Hmm.
So because it's a one-to-one function, I can use change of variables, that particular those equations that I shared with you, to get an understanding of what that distribution looks like. So this g function is different, plays a different role than this f function. Again, f function is the PDF of the original random variable. This g of x is the transformed random variable, and the y has PDF some f y, where f y is going to be the Jacobian times f x at y.
Okay. So in this case,
Okay,
it is, since it is a single variable here, both of them are going to be same, right?
both of them are going to be same as in.
In the sense
Oh,
like,
in this case,
uh-huh. Let's say
yeah. Go ahead.
if the PDF is in single variable, in the lecture
Yeah, yeah. This is by joint. Mhm.
we were in the two variable space, d theta
Yes.
and xy.
Yeah.
That's why we had a matrix over there. Uh, but here,
Ah,
is it
here,
like
here, here, this Jacobian is not going to be a matrix anymore,
hmm,
right? It's going to be just a absolute value of a scalar quantity, right? Which is just going to be the derivative of the mapping with respect to x,
so that is
with
going to be
respect to y.
1, is it here? Dx by, is it going to be
No, no.
derivative
Oh,
with
well,
respect to x?
in this example, yes,
Hmm.
yes. So in this example, yeah. So in this example, f of y is going to be absolute value of partial derivative of x. Uh, so del by del y. So this is going to be y minus 5 by del y. So I look at the opposite end
Hmm.
because the final object has to be a function of y, right? So I have to look at the
Right.
final object. So this is the not partial but full derivative. And f of y, sorry, f of x at y, which is x minus, sorry, which is y minus 5.
Hmm. Okay, got it.
Now this, like you said, I correctly identified, this is just 1. So this is just f of x, y minus 5.
Okay.
Okay.
Okay, got it. Yeah.
Yeah.
All right.
Now, again, what is the source of this? I mean, I'm not sure if this happened in your first probability stat course, but
No, it didn't happen.
that's like a law. Okay, so I mean,
Uh,
I would have expected that too, but it's
uh,
I'm surprised to know. Yeah.
Actually, ma'am, this has happened in stats too, and in MLF also for two random variable it is done.
No, no, shift.
Okay.
I mean, it was not in the context of shifting of densities, right? I mean,
I mean, but you can define this function of as anything, right?
okay, maybe general linear algebraic transformation. Is it?
Not linear algebra, right? Any one-to-one function, right? So any one-to-one function. So log,
Okay, okay. Maybe I'll get back to the
for
notes.
example, right?
I think I understand it
Yeah,
right
yeah,
now. Um,
yeah. Okay,
all right.
okay, good.
Yeah. One more question was around the first question in the graded assignment. I think we are already past the deadline. Can we discuss that the first question that we have in the graded assignment? So we have a
Okay, sure. Let me
target proposal f of
stop
x.
sharing my screen
Yeah.
1 second because I don't have it in front of me right now. Nikita, would it be possible for you to
Yes,
share the screen for me to see it?
yes, ma'am. Yeah.
I went through the calculations couple of times. I think I'm getting some um, unexpected results, like in the sense like
Okay.
the optimum value for x. I've got one equation, but optimum value of lambda I'm getting as negative, but for exponential lambda
Ah,
cannot be negative.
yeah, yeah. So let's see. Let's check. Let me just go make
Yeah,
sure I
I'm
understand what the
sharing.
question is. Mhm. Should I find it? Maybe I can find it in my email somewhere.
Oh, no, no, it's there. I shared the wrong page.
Okay.
Yeah, this question. Yeah. Oh,
Okay, first
go.
problem.
Yeah.
Find the optimal value of lambda. Enter the correct answer to 3 decimal places. Okay. So how did we try doing this, Govind?
So what I did is the proposal distribution is exponential. That is the PDF is lambda e to power of minus lambda x. C of lambda is 1 plus x e to power of minus x by 2. I mean that simplifies to 1 plus x e to power of minus x to the power of 1 minus lambda by 2 lambda. Taking natural log on both sides to get rid of exponential. I've got x optimum value of x as lambda by 1 minus lambda.
Okay, wait. Let me see if I can follow the argument. So let me just write down this question once, and then I will ask you to stop sharing screen, Nikita. Okay.
Yeah.
I have f of x to be equal to 1 plus x e to the power minus x by 2. Yes. And then g of x is just exponential.
Exponential.
Yeah. So this is this is f of x, and g of x, this is
Lambda
x greater than 0, is lambda e to the power minus lambda x. Right?
Right. This is also
Again,
for x greater than.
Yeah. So basically, I need to find soup to implement accept reject. I need to find a bound soup of x in script x, which is basically over the support, which is x greater than 0 of f of x g of x.
Yes.
And this number that I get should be a function of lambda. Right? So now this is, so let me, instead of this, what I'll do is I will just take into account f by g only. Okay, and then I will maximize it. So consider r of x to be equal to fx by gx, right? Which is 1 plus x e to the power minus x by 2 lambda e to the power minus x. And like you're correctly saying, that it's much easier to take log. If I take log of r of x,
I took natural log. I think anything could be taken, right? And then to get rid of
anything could be taken, but typically, usually, I think unless there are other powers like 10 to the power, 2 to the power something, then log base that is useful. Natural log is what's useful. When I write log, I mean natural log. Okay. Typically, that's common in statistics. Okay. So this is this becomes log of 1 plus x. Okay. Minus x plus lambda x minus log 2 pi.
Plus lambda. Yeah.
2 lambda, sorry. Yeah.
Yes.
This is fine. Okay. So now what did you do?
I took the derivative with respect to x.
I took the derivative with respect to x. So I do d log r of x by dx. So this is 1 by 1 plus x
minus of
minus
1 minus lambda.
Plus lambda, right? Yeah. And then I set it to 0.
Right.
Right? So this implies lambda minus 1. I always do this incorrectly. So 1 minus lambda is equal to 1 by x, 1 plus x.
1 plus x. 1 plus x equals to.
Yeah. So 1 plus x is equal to 1 by 1 minus lambda. So x is equal to 1 by 1 minus lambda minus 1.
Right. Comes to lambda by 1 minus lambda.
And I always, yes, I always want to be careful. I want to write x star now because I've set it to 0. So I'm talking about the optimum value of x. So this is, 1 minus 1 plus 1. So lambda by 1 minus lambda.
Yeah, correct.
Right? Okay, very good.
And double derivative is also negative.
Very good. So then d log r x d square divided by dx square, you've checked, I'll believe you, is 0.
Minus 1 by 1 plus x x whole square.
Okay.
Because x is greater than 0, it is negative.
Correct. So very good. So now what I do is to find C lambda, it is nothing but f at x star by g at x star.
Yeah.
Yeah.
Correct.
Okay, very nice. So then I'll put this back. So this becomes, so this is 1
1
plus x
plus
star. I like to do all my steps. Okay, so I'm a little okay, because I have made too many mistakes in my life, not doing all the steps. Okay. So lambda x star, correct? If
Mhm.
I'm okay. So now 1 plus x star is equal to 1 plus lambda by 1 minus lambda. Okay. E to the power minus lambda by 1 plus, sorry, 1
1 minus lambda.
minus lambda. Okay. 2 lambda e to the power minus lambda square by 1 minus lambda.
Okay.
Yes? Okay. The first thing I noticed, by the way, here is that lambda has to be less than 1. Right? Only then the maxima actually will occur. Only when then the supremum actually occurs.
Correct.
Right? So
That
that's
is correct.
something to keep remembering, right? Otherwise, the soup doesn't even occur and we can't actually use the proposal.
Right.
Okay. So then now let's solve this even more. So let's see what we get. So this just becomes 1 by 1 minus lambda,
Mm.
right?
2 lambda.
2 lambda. E to the power minus lambda by 1 minus lambda. But I can take that comma. So let me actually do this differently. So I can actually do this as exponential of minus lambda 1 minus lambda. And there's this part and this part have some in common, right? And both are in exponential. So then this becomes 1 minus lambda,
Right.
right? So then this goes away. Yes?
Yes.
If I'm not wrong, yeah. Then
that's
this I just get 1 minus lambda, 1 by 2 lambda, e to the power minus lambda. This is C lambda.
correct.
So as long as I for lambda less than 1.
Right.
As long as I choose lambda less than 1, this is my supremum. This will be the expected number of loops for my exponential algorithm, for my exponential proposal.
Right.
Right? Okay.
Now we have to
To find the
differentiate.
optimal, yeah, exactly. To find the optimal proposal, I want to minimize this. C lambda is a function of lambda. So again, I take log because I can see that taking log will make my life much easier. So log of C lambda is minus log of 1 minus lambda,
Hmm.
right? Minus log 2 lambda minus lambda. Yes. So I take d log of C lambda by d lambda, which is minus 1 by 1 minus lambda, but another minus will come. So this will become positive.
Hmm.
Yes. Minus 2 by 2 lambda minus 1. Yes.
Yeah.
Okay, very good. The steps here agree with what you've had so far?
No, actually, I did not take log here. I took derivative directly.
This is the, this is so many hours get wasted by all of us because we forget to take log when it's so much easier to take log. And we can take log because this will always be a positive number. So there's no problem taking log.
Yeah.
Okay, very good. So I don't know, maybe there's faster ways of doing this, but I'm always old school. So this becomes lambda. This is minus 1 plus lambda minus lambda plus lambda squared. Okay, and I feel like I've already done this mistake of doing things mental math, but it's okay. So this is lambda square plus lambda minus 1 by lambda 1 minus lambda. Then I set that to 0, right? This implies lambda square plus lambda minus 1 is equal to 0. I want to find the lambda star is the one that optimizes this, right? So lambda star optimizes this. Okay, very good. But now I'm going back to my high school mathematics. So this implies, what does this imply? This is
Lambda
lambda, I
square,
can complete the square,
yeah, plus 2 lambda
right?
minus lambda.
Plus 2 lambda. Very good. Thank you, because I had forgotten my high school mathematics. Right? Nice. Okay, so this implies this is lambda star, lambda. Oh no, this doesn't work. Does it work?
Yeah. Oh.
No, there's a 2, right?
Mm.
Or maybe we can directly use the formula.
Yeah, we can use
Minus
the
B
formula,
plus
right?
minus, yeah.
Yeah, correct. I was hoping it'll be a simple answer. So the lambda star then is minus b, which is 1, minus 1 plus minus b square, which is 1 minus 4, which is 4 by 2a, right? So 2. Right? Okay, and so there are two possible values, but I know that this number, whatever it is,
Should
it's
be
5, the square root 5. The square root 5 is greater than 1. So if I take the positive one, I know my lambda will be positive. So lambda, the optimal value of lambda star, sorry, should be lambda star is equal to square root 5 minus 1 by 2. Okay, and that number is indeed less than 1.
Yeah, it is coming out as 0.618.
0.618. Lovely. Okay.
okay.
Yeah.
I think because I did the I took the direct derivative and it
Yeah.
gave me lambda equals to minus 1.
Yeah, I think so. Most likely, when you took the direct, see, nothing changes, right? The answer should be the same. But taking the direct derivative of this thing means that you are opening yourself up to making 5 mistakes at least,
Mm.
right? Because, chain rule, product rule, all of those things come in, and somewhere we end up making a mistake.
Yeah.
Yeah. So always, and this going forward in our other, as we get to the future part of the course, when we get to optimization methods, we have to take derivatives all the time, and we must, taking log must be our default.
Yeah, sure. Okay.
Okay.
I think you emphasized it many times in the lecture.
Yeah.
I didn't see it coming in this form at this stage.
Yeah.
I took it in the
No,
in
no.
the in the
In the
beginning.
past, yeah, exactly. That's okay. That's
Okay.
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 Very good. Okay. Anything else, Govan?
I think that's all I had, ma'am.
Okay. Excellent.
So one minor thing, I think we in the bound calculation for f of x by gx for an indicator function, because indicator function is 1, probably we took it as in the bound calculation. I think
Mm-hmm.
I think that is fine. I think I understand that.
Yeah. So indicator function is not one. Indicator is function either 1 or 0.
Hmm.
So the largest value it can take is 1. So it's
1.
always bounded above by less than equal to grid. It's always less than equal to 1.
Right. Okay. Sure. Yeah. Got
Yeah.
it.
Yeah. Okay. Very good. Okay.
Yeah.
In that
Yeah.
case,
That's all.
Nikita, I think is it okay to leave then, or would you like me to stay?
Oh, ma'am, I think it's okay to leave.
Okay. Okay.
Yeah.
Okay. Thanks
Okay.
again for
Thank you
Govind for
very much.
coming in.
Thank you,
Thank you
ma'am.
very
Yeah.
much.
Sure. Okay. Bye bye.
Bye.
Good night.
Bye.
Bye.
Thanks, Nikita.
Yeah, thanks, Govind. So, Govind,